Recording in progress.
All right, folks, hello. Welcome back to our conversation about thermodynamics, specifically our conversation about free energy. In our last video, we looked at how we could figure out the change in free energy of a reaction if that reaction was not yet at equilibrium or if it did not exist at standard states. And we looked at these relationships between the reaction quotient and the equilibrium constant K to determine if the sign of delta G would mean that our reaction is spontaneously going to achieve equilibrium or non-spontaneously, right? Like if that process would just happen or not. It's kind of the whole conversation about thermodynamics. Will this process just happen or not? So what I want to do now is I want to see if we can't practice utilizing this equation, meaning like actually determining whether we have systems established that would be ender or exergonic based on their free energy calculations. So let's look at an example where we have here a reaction between some gaseous compounds, and I want us to find the free energy at standard state conditions at a temperature of 298 Kelvin, and then compare that to the change in free energy of the reaction at non-standard conditions at 298 Kelvin, given information about the reaction mixture. So let's see if we can kind of predict a couple of things. So notice I haven't given us any like thermodynamic data beyond just the standard free energies of each of the substances involved in this reaction, meaning like you don't have the enthalpies and you don't have the standard entropies. But what you do have is you have the ability to maybe at least look and see if the entropy of this reaction is one that increases, right? So we've got, let's see here, 4 and 5. That is 9 moles of gas, or 6 and 4, which is 10 moles of gas. So we do expect to see an increase in entropy. That is too thick. There we go. So based on these, and then this is the S of the system, our surroundings. And then if we inspect this reaction, you might notice the structure of like something plus O2 making H2O gas. While it's not a hydrocarbon combustion, this is still like a combustion reaction, and those are typically exothermic. I mean, hydrocarbon combustions are absolutely exothermic, but we suspect exothermicity, which would mean if we are increasing the entropy of the surroundings and also exothermic, then just conceptually, we might be able to predict that delta G is negative, meaning we are spontaneous. But let's see if we can't figure that out. So I've got our standard free energies for each of our substances, and I want to determine the change in free energy of the reaction at standard conditions, given the temperature being 298 Kelvin. So let's start with part A. So in part A, we need to figure out the change in free energy. So this is going to be the difference in our free energy values from reactant to product state. And notice all of this thermodynamic data that's given for our standard free energies is given in kilojoules per mole, implying that this is the amount of energy that is absorbed or released when 1 mole of substance is being created or reacted. So I have to take into account the stoichiometry of this reaction. So I'm going to say that the change in the Gibbs free energy at standard conditions, which is going to be found from the standard free energies of each of my substances, is going to be the sum of the moles of product times the Gibbs free energies of the product minus the moles of reactant times the Gibbs free energy of reactants standard. So let's take a look here. Our products. This is this side here. So I've got to look at my moles of gaseous water as well as my moles of NO. So we're looking here. All right, for water vapor, I made 6 moles of those. And the free energy of water vapor is negative 288.6 kilojoules per mole. So that term plus, so if it helps, I kind of like to do this in like brackets and extra parentheses. So that's one product. Plus the other product, that is our NO. So that is going to have 4 moles of NO times its standard free energy, which is 87.6 kilojoules per mole. Okay, so we've taken care of our product terms. Now we need to look at our reactants. So we need to subtract out the reactants. If you want to do this like we did in my Gen Chem 1 class, where instead of subtracting out the reactants, you simply add them but flip the sign, that's totally fine too. But let's see, doing the traditional way, what we get. All right, so reactants, we had 4 moles of ammonia, and ammonia has a standard free energy of negative 16.4 kilojoules per mole. Plus, and lastly, oxygen. This one's nice and easy. It's an element, so it's thermodynamic data, except for its free entropy. Well, no, yeah, element's always going to be 0, so that's going to be 5 moles times 0 kilojoules per mole, just so we can see where that came from. And when I do all this math and put it back into joules, I get negative 9.56 times 10 to the 5 joules, or negative 9.56 times 10 to the, let's see here, take away 3, 432, so that'd be negative 956 kilojoules. Is our standard free energy change. And notice we predicted that this would be something that is spontaneous, just kind of using like our chemical intuition about, all right, we've increased the entropy of surroundings by making more product gas moles than we had reactant moles. And then also this looks like a combustion, and those are typically exothermic. They're exothermic. And lo and behold, when we do our calculation from our standard free energy thermodynamic data, we do see an exergonic process. So this would be spontaneous at this temperature, 298 Kelvin. Now B, that is asking for us to determine the non-standard free energy change, given information about the reaction mixture before it's reached equilibrium. So let's remind ourselves of the equation that allows us to determine the change in free energy for a reaction at non-standard conditions or in non-standard states. So remember, this is equal to a correction to the standard Gibbs free energy plus a term that takes into account the equilibrium, not the equilibrium constant, the reaction quotient, right? Now here we were not given a reaction, an equilibrium constant, so we couldn't like just look at the equilibrium constant, compare that to maybe a perhaps calculated Q, and then predict the spontaneity of this reaction, we actually do have to calculate this and see if anything has changed. So first of all, this is what we calculated from earlier. So this is our, let's keep it in joules, negative 9.56. Whoa. Negative 9.56 times 10 to the 5 joules. And that is an implied joules per mole, per 1 mole. All right, R, this is 8.314 joules per mole Kelvin. T, we were told, is 298 Kelvin, which means that we have everything we need except the reaction quotient. So let's determine the reaction quotient in the mixture, provided that we are like told that these are the pressures of our reaction mixture, but it doesn't necessarily mean that we're at equilibrium. Like you'd have to be told these are the equilibrium pressures. Now these pressures are in bar, which is fine. Bar is becoming or is the standard pressure. We probably should have done KP in terms of bar instead of atmospheres, but they are close enough-ish for us to for now say they're the same. So I'm going to just write out the Q expression. This is going to be products raised to their coefficients over reactants. So this is pressure of H2O raised to the 6 times pressure of NO raised to the 4 over pressure of O2 raised to the 5th times pressure of NH3 raised to the 4th. So that is going to be, okay, pressure of H2O, that is 1.5 bar raised to the 6. Pressure of NO, wait, hold on. Yeah, NO, 1.2 bar raised to the 4th. And then pressure of oxygen, 1.0 bar raised to the 5th. And then we have, let's see here, pressure of NH3, which was 2.0 bar raised to the 4th. All right, let's see. What do we get when we find that actual reaction quotient value? So to the 2 sig figs that I'm limited to, I get 1.5 as my reaction quotient Q. So this reaction quotient is what needs to go inside my natural log term in this correction to find my free energy at my non-standard conditions. So then we get delta G is equal to negative 9.56 times 10 to the 5 joules, presumed per mole, right? Plus RT, remember R, we are using the gas constant that uses an energy term, so not 0.08206, that's liter atmospheres. We're not looking at pressure volume work. We want an energy term in joules, so it's just a conversion. So this is 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of 1.5. So here we've got what? Let's see here. When we calculate this out, what do we get? All right, you will notice that this is not a huge change. When you do this, you get negative 9.6 to 2 sig figs times 10 to the 5th joules per mole, or negative 960 kilojoules. So it looks like at these reaction conditions, this mixture, this would imply going back here, that since we had a spontaneous drive, like we got a larger negative delta G, right? The magnitude was larger and the sign was negative, that we would be driven toward equilibrium spontaneously. So our reaction quotient is not one that exists what am I trying to say? Not one that exists like post reaction, right? Like we've got all the pressures and relative amounts that give us like before equilibrium it's been established conditions. Okay. So that is how we apply our equation for non-standard free energy change. And last up in our conversation about thermodynamics is how do we put this all together, right? Because again, the theme of Chem 220 is talking about equilibrium. So if I want to figure out like the spontaneity, aka the change in free energy sign, I want to relate that to some temperature and also relate that then to the enthalpy and entropy of some kind of reaction. I need a mechanism of putting that together. So let's recall that the standard free energy change for a system at equilibrium is equal to negative RT ln K. And we've also said that the standard free energy change of a reaction is related to its enthalpy and entropy at some temperature by saying this is equal to delta H reaction minus T delta S reaction. So these are equal expressions when a reaction reaches equilibrium or exists in a state of equilibrium at standard conditions. So let's set them equal. Let's see what we get. We have negative RT ln K is equal to, so this was our first expression of our change in free energy, is equal to delta H reaction minus T delta S reaction. And again, chemists really like to have straight lines, right? We want a y equals mx plus b. So let's try to see if we can't answer the question. How does K, the equilibrium constant, depend on temperature? And this is what we looked at when we did our KSP and solubility of borax lab, right? So let's isolate that natural log K because that is a term that relates K. So I'm going to take my natural log K and have that on its own by itself on the left-hand side, meaning I'm going to multiply over my negative RT. So this becomes, sorry, not multiply, divide. So this becomes negative delta H over RT minus T delta S negative RT. So just note, keeping my negative here and here. This is going to make us a positive, and also we're going to see that temperatures cancel. So this is going to become positive. Temperatures cancel. So we get negative delta H over RT plus delta S over R. And again, we have now the left-hand side, the dependent variable, something about K. And now we want to figure out the independent variable. Like if we change this, the K is going to change as a result. And that thing is, again, temperature. So if we're looking at like how K is going to be affected by temperature, then let's isolate our temperature term, which is in the denominator. So we get then ln of K is equal to negative delta H over R times 1 over T, where this inverse temperature, 1 over T, is just T pulled out of the denominator, plus delta S over R. And this is the equation that relates the equilibrium constant to temperature and other thermodynamic data. So this is kind of nice because if you can get this, then you can determine ln K, which will allow you to then determine the standard free energy change. All right. So that is it for thermodynamics. Coming up next, we're going to talk about the how of chemical reactions. If thermodynamics is the why, then chemical kinetics is the how. So that's coming up in our next topic. So see those videos posted soon. Thanks, folks.